So, hello. Can you hear me? Yes. So my name is Tobias Lindahl, and this talk is sort of a rough version of the talk that Erik Happy Stenman is going to give in San Francisco in a couple of weeks. And he asked me to give this presentation today. So apparently, yeah. So it is really his presentation. I will take no credit for anything. So I've been, apparently Ulf beat me with 10 years about in the Erlang world. So I've been being a full-time Erlang programmer since 2002, where when I joined the Hype group in Uppsala University. During that time I wrote the dialyzer. So any beef is kept within the Eternity team. And then I joined Klarna together with Happy some 10 years ago, and then we quit and started our own company, Happy Hacking. And since September this year, we work with Eternity. So the motivation, Janni more or less covered, so I will not stay on that. And why are we using Erlang and or Elixir, that we also covered. This is the team. Happy is very proud of his CSS skills. I think the main takeaway here is that we were pretty experienced Erlang developers, and for whatever reason that Erlang was chosen to be the core technology for Eternity. They have managed to collect a pretty decent team, and we're more from the Erlang world. We're more Erlang experts than blockchain experts, but we have some really good blockchain experts to compensate with there. Okay. So in Eternity, we have these features. We have the Oracle names. We have all these guys as first-class objects. Instead of having to implement the oracles, for example, in a smart contract, they are really on the chain. You can refer to them, you can use them directly, you can use a transaction, you send the transaction to the chain, where you define an oracle, where you provide the sort of the real-world data and so on. So, and in the contracts, which are really programs, right? You can refer to all of these guys directly. And that's sort of the difference with Eternity, right? So you don't have to sort of build, there's a lot of infrastructure around these objects that you can reason about directly instead of having to implement them first. It's just like the concurrency in Erlang, right? You have a lot of built-ins, okay? So the oracles is supposed to bring in information from the real world, from the outside world. So the data is structured. You register an oracle and then you announce it in some way. If you find an oracle, you can build a contract that refers to the oracle answer in order to have some outcome. And the oracle answer is the data, which is structured. So you have a type of the oracle response, so you know what kind of information that you're going to get. But on the other hand, you can provide the complete work of Shakespeare if you choose to, and it will be a string, right? But you can also do a Boolean oracle, or you can do an oracle with that sends back whatever, but you know what it will send back. We have names. So this is basically that you assign a human readable name for anything on the blockchain. You can name an oracle, you can name an account, you can name whatever of the first-class objects. And it's basically like a DNS. So you can refer to the names, it will be resolved, and you can use that in your contracts. Tokens, we have native tokens on the blockchain. You don't need to keep the tokens in the contract, or you can refer directly to the tokens, right? Governance, voting on stuff on the blockchain, you can refer to the actual sort of voting object. So you can refer to that in the contract as well. We have the state channels. Right. So should we stay a bit on the state channels? Does everyone know what the state channel is? Okay, so let's stay a bit. So one of the problems with the scalability for the blockchain is that you need to submit your transaction to the chain. It will take some time for it to be included and so on, and it really takes a lot of time to get your transaction through. But if you know some other party that you need to do some rapid transactions with, and you can open a state channel with that other party. And then you do whatever transaction you want. Both of you sign this outcome of this, and you put it on the state channel. And in the end, when you're sort of done, we have done enough transactions in between of our, you submit the final state of the state channel to the blockchain, and it gets accepted, right? So in that way, you don't need to wait for the transactions to get accepted to the blockchain. You can just handle it without outside, and you don't need to sort of bother all the nodes with your transactions until you're done. Okay. And then we have the contracts. So the contracts is really programs that are running on the chain. Every miner will run the contracts and verify the outcome of the contract. And in the contract, you can write these programs that refer to the chain and to the other objects on the chain. So this is really the topic of this talk. So these are the goals of our contracts, the design goals. I'll go through them one by one. So goal number one, the contract execution should be safe. So you can have attacks on contracts. You find weaknesses in contracts and you exploit them. You might have an integer overflow, or you find weaknesses in contract. So once you have submitted the contract to the chain, there's a bit of insecurity in that someone will steal your money, right? So in order to be safe, we are designing a new contract language, or rather two contract languages. The main one is Sofia, and we aim to be able to prove stuff about this. We want to prove properties about Sofia in order to increase the security. And also we have a FTW VM, the virtual machine, that will check some more stuff for you. Goal number two is to have an efficient and scaling contract execution. And really the scaling is going to be, scaling of the whole blockchain is not going to depend on the efficiency of the contract execution, but rather on the consensus algorithm and the state channels. But we want the contract execution to be efficient as well. So in order to solve that, we are designing another language as well for the high-level stuff, where you can do a bit less, but you can do it blindingly fast, and you can do it. And you can reason about the cost of executing that contract. Yes, which is goal number 3, by the way. So it should be cheap to execute the contract. And now, when you know upfront, if you use that language, you can know what kind of cost is associated with running this one. This is a problem in another contract execution. So Ethereum smart contracts are quite popular, or at least they are very common, at least. And we want it to be easy to migrate from your Solidity contracts that is written for the Ethereum to Eternity blockchain. So that's why we also have the Ethereum VM supported in the Eternity VM. Okay. So we are building a version of the Eternity VM, Ethereum VM in Eternity, the AEVM, so that you can basically take a contract written in Solidity and run it on Eternity. We are improving the Ethereum VM somewhat. So, for example, the self-destruct instruction in the EVM will destroy the contract, but we will have some kind of reference counting to the contract, so it will be marked for destruction. But if you have other contracts referring to that contract, it will not actually be removed until there is no references to that contract. We're using Blake 2 instead of SHA-3 for hashing. We have subroutines. And there's a limitation currently in the EVM that you can only access 16 stack positions. So we have instructions for accessing more of them. And we're adding bit manipulation instructions, which is coming into the EVM as well. So, Sofia. This is sort of the more expressive of our new languages. So it's a typed functional programming language, and it's basically an ML, and it's very close to Reason. And Sofia can be compiled to the safe virtual machine FTW VM. I will come to the acronym at some point. And it's, yes, which gives it more safety concerns. So Sofia provides ways to define properties, and these properties we want to prove that they are hold, or if we can't prove that they hold, it will result in a compile time error, giving you the added security. So this is actually a, let's see, yes. This is a Solidity contract ported to Sofia. So this is how it looks. I will not go through this. But it's pretty, isn't it? It's wonderful. Right, the Sofia compiler is typed, and it keeps the types all the way down to the bytecode. So the problem is for when you compile your program or your smart contract, you will end up with bytecode, and then this is the bytecode that you will send to the chain, and everyone will execute this. So this gives you, if you're the writer of the contract, you can compile it with the compiler, and you get all the properties that you want, but you also want to be able to provide the security to anyone who is calling this contract. And for that reason, we want to keep the type information in the bytecode as well, so that the virtual machine can actually check this as well. So the functional typed worded virtual machine, the FTWVM, is a high-level virtual machine with variable word length it should be, and associative memory. So it's functional, it's an ML. We have the tag data, we have automatic memory management, and associative memory, basically variables. It's typed. All the instructions and memory positions are typed and tagged. It's worded, and all instructions are checked for overflow and underflow and stuff like that. This is typically called checked, but apparently the acronym wasn't correct if you put a C instead of a W. And also, we're the latest addition to the property set is that we should have the instruction cost controlled by governance. So today, all instructions cost some gas to execute, and this is more or less static, and you need a hard fork in order to change that. But if we can control that by governance, we can have a more dynamic pricing of the contract execution, which is nice.
Is that an established term in the Ethereum community?
The what?
This FTWVM.
Established term in the what?
In the Ethereum community.
In the Ethereum community. No, we're doing this now. This is our invention.
So that's why Wikipedia has never heard of it.
You're probably the only one outside of Eternity that has ever heard of it. Yes, it's completely new. I'm a bit disappointed that he didn't know it already. It's in the code. It's open source. You can read it. Anyway, so the second programming language that we're developing is called Varna. So it's Sanskrit for type, and it's a much more high-level language. So basically, you have no looping. You can compute the gas cost at compile time. At least you can do a interval, sort of an upper bound on the gas cost at compile time. But it's still quite powerful since we have all these first-class objects. So you can do this, for example. You can refer to oracles, you can refer to tokens, and you can refer to other contracts like that. So this one would be a Varna contract for buying some tokens. So in a way, never mind. Okay, so it's very nice. This acronym you will not find on Wikipedia either, and we haven't really decided on that one. The high-level machine, the HLM, it's not a really good one. But anyway, this is the virtual machine that Varna is compiling to. So it will be very fast, and it's as fast as sending some transactions to the chain. So this would be a symbolic version of the Varna bytecode, basically. Yes, I guess this is probably the same contract as you saw in Varna before. So this is the Varna code that you would write. This is what it would compile to, or rather, it would compile to some kind of bytecode. But this is the symbolic version of that bytecode. Yes. Some acknowledgement and open for questions. Yes?
Fees, are they earned or are they distributed to miners or?
Sorry?
Fees for contract execution and such. What happens with it?
Yeah, well,
Earned or are they?
yeah, they go to the miner, right?
Yeah, they're not earned or any goes to miner.
Yes. Yes?
Why did you have two virtual machines for like a single blockchain? And like how are they related to each other?
So the virtual, so you have the AEVM, which is the virtual machine that you can run Solidity contracts on, and that Sofia will probably compile to as well. You can compile Sofia to that. So I guess that we want to be able to call Sofia code with from Solidity, for example. So if you would take your Solidity contract from your Ethereum library and then if you need to do some specific stuff that is specific to the Eternity blockchain, like calling an oracle directly or something like that, you could write that in Sofia, and then you would call the Sofia code from the Solidity code, and it might be beneficial if this is for the same VM. And also we want to be able to compare the Solidity contracts and the Sofia contracts, right? But the aim is to have the added security of the FTW VM for the actual Sofia VM. So then in the end you probably be I think you can choose at transaction time which VM to run on. So this is. They will be very similar probably. So, but there will be all the tag checking and stuff like that don't exist on the AEVM, but will exist on the FTWAM. But a lot of things will be the same. And then the third virtual machine, which is hardly a virtual machine, the HLM for the Varna language. Okay. Yes?
Question about the state channel.
Yes?
I assume that in order to get the throughput boost, you need a fair amount of this transaction to happen on the channel rather than on the chain.
Yes.
Do you have an
Yes.
idea of the proportion that you are expecting to run off-chain?
No, I don't. Does anyone?
Your colleagues?
Yes, the question is how much of the transactions will be running on state channels rather than on the chain?
So we talk about use cases like micropayments or videos or music. So each frame can be paid by micropayment. So in a movie you have like millions of frames, and it's internal to the contract. No, sorry, the state channel. All right, maybe now. So let's this example once again. State channels would be good for example, streaming movies or music, and we can pay for each frame. So it's thousands or hundreds of thousands transactions, then wrapped up in 2 transactions for channel. So.
As I understand that this makes all the use cases possible, what they would be.
Well, these use cases are not practical on on-chain in on-chain version.
But you haven't estimated a proportion that you are expecting to run.
What
Based on the use cases, let's say.
based on the use cases? Well, we don't have live user base. We could take Ethereum and reason about that based on Ethereum, but I guess we didn't do it yet.
What kind of problems are you anticipating? Because you're opening a separate channel, and the other
Right.
stuff is happening on the main chain. When the transaction gets completed, it needs to come to the main chain. So, and then there is, as you say, like, you know, say for instance, a movie has 1 million frames.
Right.
You and I have transacted for say 10,000 frames, and I'm agreeing to pay for that. But the chain has moved on. Then at what point does that come?
So the question was about possible problems when it's a long-running state channel and we transact in it, and what can happen, I guess. Actually, it has pretty good theoretical background.
So what problem are you? So it's going to be one transaction to open the state channel. Then you can have arbitrarily many transactions on the state channel, and in the end, you just submit the final state back to the chain. You don't submit the whole shebang,
But
right?
where does the history of all the transactions?
It's gone. It's only in the state channel.
It's only in the state channel. So once the state channel is complete, the history goes away.
Yeah, you can keep it around if you like it, but you don't. It never enters the chain.
Thank you.
Hmm?
What's the security then like of the state channel? I mean, how do you guarantee
So the question is, how do we guarantee the security on the state channel? Well, every news. So basically, if you and me open a state channel, and then we sign, multi-sign. Both you and me are signing all the states on the state channel. We do a transaction. You and me sign the outcome of this transaction, and in the end, since both of you have signed it, this is the security. And then you can, of course, you can try to fool this. You can take an earlier state that is more beneficial for you and submit that to the chain. But then you have the possibility to actually send, the other party has the possibility of sending the proper outcome of this state channel.
And are they written in the same two languages, the state channels?
So state channels is not written in the language. You can probably have contracts associated with state channel, but the state channel is more like a side chain, if you will, just a series of signed states.
And who stores the state channel then? I know you said it gets destroyed, but who intermediately stores it? How many nodes is it distributed?
So the question is, who is storing the intermediate states? Well, both of you are. It's in both you and me are storing the states because it's in our mutual interest to store it. And if we want to send it to someone else for safe storage,
So what's the difference between just making the whole thing off the network entirely and then just putting it in at the end? Like, what's it giving you that just being completely separate to the network?
yeah. So what is this giving us? So when you open a state channel, you will freeze some funds into that. You will have some funds on the main chain. You open the state channel, you transfer. By opening the state channel, you're locking that fund there. So that is and the rest of it, nothing needs to be seen by the network at all. You can keep it totally separate. You can write it on paper or whatever, and in the end, you submit the final state, which unlocks or sort of distributes the original locked tokens back to the chain.
There's no way of storing it in the network. Because if you've got two, if you've got two smartphones and one goes offline, surely both parties have to just throw everything away, because it's not like if something's been consistently written into the blockchain, it's there, and if one party disappears, the data's still there, sort of all the intermediate stages.
Well, if you lose your private key, your funds is locked as well, right?
Yeah.
So this is the same thing. You need to store it somewhere safe.
Okay.
Yes.
Okay.
So if it happens that some of the nodes on the chain wants to make it a business model to store that for you, fine. This is a good business case. You can do that.
Right. Okay.
Just have one. So what is the efficiency gain you anticipate by having the state channel?
What is the efficiency gain from having a state channel? Well, basically, you don't have to wait at all for doing the transactions with the parties on the state channels. That's a pretty huge efficiency gain. Sorry?
Latency reduction.
Yeah, latency reduction. You have immediate trust, if you will. No fees. No fees. Of course, it doesn't cost anything. So that's not efficiency. It's just a benefit.
Slide. So two people store the state channel. You may have answered this question before, so I apologize if you really I missed it. But if those two participants disagree on what the state of the state channel is at the end, who resolves that?
So you have a final. You will have sort of the final double-signed state. So if you disagree, you will not sign the other state, and this is not a valid state. It's as simple as that. Yes?
Who opens the channel? Is it both parties? Is it one party that opens the channel, or?
No, you have to sign it. Both parties need to sign the opening of the channel.
And does that also for the closing? Both parties are needed.
The closing is just submitting the final dually signed state, and anyone can do that.
So, yeah, either one can close.
Yes, I would say we haven't actually implemented that yet.
Okay, because
But
if
I would expect it to be one transaction that the one that actually sends it
the last
will,
one.
yeah, the one who gains the most likely, right?
Okay, yeah, because otherwise,
It's not in my interest if I paid you a lot of money. It's not in my interest to send this state to the chain.
No, that's what I'm talking about. Because
Yes.
if both parties are required to close it, if one party walks away,
No. So this is really the crucial point. Since you have both have signed the state,
the opening.
both the opening and sort of the final state, you're already done. You have signed it. You have accepted it. So then it's just a matter of getting that one back to the chain. No more questions?
What if you're sending, so if one party opens a state channel, so if I'm sending to an exchange, what would the...
One party opens the same channels. I think
Yeah.
both parties need to, since you're locking funds for both parties, you need to sign it both the opening of the state channel. Right. Other guys, you need to correct me if I'm wrong, but
I'm trying to think if you're sending, say, to Binance or Coinbase or something, they're not going to have a state channel open, per se. What would the TPS be without the state channels?
what would the TPS be
Transactions
per second without the state channel?
without the state channels.
I have no idea. Do we have an estimate on that one?
It depends on the block size, which is governed by the governments. So
Yes.
this could change. People can vote to change.
Yes. Yes.
So what's the procedure for opening up one of these channels? How does that come about, like, for two people to come together and say, open this channel, like, where it's two people needed?
So you need to both sign the opening transaction. That's
So
where.
who initiates this process?
Yeah, it can be either one, I guess.
So, like,
So it's up to you and the other party to decide how you're gonna actually double sign the transaction.
that's what I mean. Is there some kind of time frame that it needs to be done in? Like, what's the actual process? Like, say I went to open up a payment channel with somebody, and I initiate my side. Do I have to give them a phone call to tell them to initiate their side? Like, how does that work?
Yeah, I haven't actually thought of that. So I delegate that answer to anyone else in the team. Yes. If the big boss is going to explain.
The point of the payment channel is that anybody can open it. So the payment channel happens apart from, well, the initiation of the payment channel happens off-chain, meaning that two parties come together, however that happens, and somebody has to initiate the process saying, okay, I'm sending you an initial request, this is the payment channel I want to open with these sort of variables, or sort of, variables. And if you agree, then you can sign the transaction, then I'm going to sign the transaction, then I'm going to broadcast the transaction to the blockchain. And if that is, of course there are timeouts involved and errors and everything. And so if you, for example, you can say, I want to connect to you, and I give you, I don't know, a day to respond. And if you don't respond within a day, then just nothing happens. If you already have committed money into the channel, and the other party doesn't respond within a day, then you can claim your money, your half of the money, and everything is fine again.
Right. So I still need to, like, would it be able to, like, build that into the actual protocol or into the wallet that you'll be using
Yes.
to, like, have some kind of blinking light to say that you've got people that
Exactly, yeah. Yeah, that's the idea.
Yeah.
It says you have some sort of basically client that can talk to any other client, opens an encrypted connection, and then they initiate the protocol, which again, to open the state channel needs both parties to sign the initial transactions. And how they find each other, that's a problem, but not so much a problem of the state channel itself, but a high level problem then.
So everyone seems satisfied now. Okay, thank you.